With Pasco's wireless rotary motion sensor, you can capture the rotation of objects and see how their motion changes over time, visualizing rotational kinematics like never before. The Pasco wireless rotary motion sensor makes it easy to study rotational motion, both qualitatively and quantitatively. It features a 3-step pulley and an angular resolution of 0.18 degrees. The sensor connects wirelessly via Bluetooth or through USB, so you can easily use it with either SparkView or Pasco Capstone software. Let's set up our experiment. We'll be using the wireless rotary motion sensor with an Atwoods machine to help us explore rotational kinematics and motion graphs. We have 2 hanging masses, 100 grams and 110 grams, connected by a string running over the pulley system. We'll use the wireless rotary motion sensor to measure the rotational motion of the pulley as the masses move. We'll release the heavier 110-gram mass and let gravity pull it down. What do we expect a graph of the angle versus time to look like? Let's start collecting data in SparkView and see. We see that the motion forms a parabola. This is because there is a non-zero constant angular acceleration as the heavier mass moves downward, which causes the pulley to rotate clockwise. But what if we want to understand the translational position of the 110-gram mass? We can switch our graph axes to track position instead of the angle. Now we see that the position graph is also a parabola, reflecting the constant acceleration. Since both the rotational motion of the pulley and the linear motion of the mass are related, we see that both graphs share the same shape. Pasco software automatically calculates translational motion using its built-in knowledge of the pulley circumference, which can be changed in the hardware setup properties. Now let's look at the angular velocity graph. The graph forms a straight line due to the uniform angular acceleration. What would change if we gave the heavier mass an initial upward velocity? See how both graphs are linear, with a visually similar slope representing angular acceleration. But notice how run 2 starts with an initial angular velocity. The motion starts in the positive counterclockwise direction, but slows down due to the downward force from the mass. Once it stops and changes direction, the rotation is now in the same direction as the clockwise angular acceleration, so the pulley speeds up. We can determine the angular acceleration by finding the slope. Our angular acceleration is around -19 radians per second squared. There are many possible experiments to try with the Pasco wireless rotary motion sensor. From rotational kinematics to angular momentum, this sensor is perfect for hands-on learning. For more experimental options, check out the Pasco rotational inertia accessory for deeper exploration of rotational inertia and angular momentum. To find more information on experiments and accessories, visit the sensor's product page at pasco.com. Thanks for watching and happy experimenting with the wireless rotary motion sensor.